Hi, my name's Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about how we calculate enthalpy change for a chemical reaction. The first thing I want to talk about is kind of like the basics, okay? So I'm going to use this chemical reaction of where A is changing to B, okay? And there's some fundamentals that you need to know about enthalpy, and that is when we form compounds, these elements are coming together and they're forming bonds, and when they do that, they tend to release energy. For example, if I was talking about forming the compound A from the elements, there's a certain amount of enthalpy change that would be kind of released when the formation of these bonds occur. Let's say that enthalpy change is going to be 25 kilojoules. As you notice, I put a negative sign there to represent that the energy is actually being released when we form this compound A, okay, from its elements, okay? And then we do the same thing. We look up how much energy is going to be released to form compound B. And the way we look this up is typically in some type of appendix or where it has like a whole bunch of thermodynamic values, and that's where we're looking up this information. So I'm not just creating this out of the top of my head. But let's say I'm doing element or compound B, and when compound B from its elements forms the compound for compound B, it's going to release 75 kilojoules, okay? What we can do with this information is actually calculate the enthalpy difference between compound A and compound B. And that's actually what we're trying to achieve, okay? We want to figure out not the enthalpy change to form A or the enthalpy change to form B, but the chemical reaction from A to B. And if we know A's position from the elements, and we know B's position from the elements, well, the difference between the two will tell us the enthalpy change for that chemical reaction. So the way the formula works, okay, the change in enthalpy for the chemical reaction is simply the products minus the reactants. So what we're going to do is we're going to sum up the enthalpy changes of the products, where that P stands for products, and we're going to subtract it from the sum of the enthalpy change of the reactants, okay? Well, we said that the products, B, is going to be negative 75 kilojoules. That's its position. And we subtract that from the reactants, okay? And the reactants is compound A, which is negative 25 kilojoules. And if we take negative 75 kilojoules and subtract negative 25, remember when you subtract a negative, that's kind of like adding, it comes out to being negative 50 kilojoules. So what we know is from this position to this position, from right here, A, to position down here where B is at, that's a change in enthalpy of negative 50 kilojoules because we knew each of their positions from the elements, okay? And that's how you calculate the enthalpy change for a chemical reaction. Now, we're going to do this for a real problem. In our last video, I showed you that enthalpy is an extensive property, and I showed you me holding a whole bunch of gas bubbles and lighting them on fire. Well, what we're going to do is we're going to try to calculate what it was the enthalpy change for that chemical reaction. And the chemical reaction that we were dealing with was methane bubbles, okay, reacting with oxygen to form water and carbon dioxide. So what I have to do is I have to go into my textbook, okay, and I have to look up all the values for the enthalpy changes from the elements to form this compound, to form this, to form this, and to form this, and then use my equation of products minus reactants to calculate that. So let's go ahead and do that right now. So the value for methane ended up being negative 74.8 kilojoules. The value for oxygen is going to be 0 because it's an element. It's not a compound. Okay. When I looked up water in the gas state, because remember the states of matter matters a lot. Okay. So negative 241.82 kilojoules for the water. And then for the carbon dioxide, it was negative 393.5 kilojoules. And I looked those values up in my textbook or in some type of appendix that has thermodynamic values in them. Okay. Now, The thing that I was saying before is that enthalpy is an extensive property, so the amount matters. Here, there's only 1 mole, so this is on a per mole basis. So 1 times this number is just going to be this number. This is going to be 2, but 2 times 0 is still 0. But I do have to multiply this one by 2, and then this one by 1. Okay? And then what we're going to do is we're going to sum up the products. We're going to sum up the reactants, and then we're going to take the difference between the two. Okay, so this one's pretty easy because this is just 0, so it's just negative 74.8 kilojoules. And over here, 2 times negative 241.82, and I'm going to also add negative 393.5. When I add all that up together, that comes out to being negative 877.14 kilojoules. And then I'm going to use this equation to calculate the enthalpy change of the chemical reaction. Remember, it's going to be the sum of the products minus the sum of the reactants. Okay, the products was negative 877.14 kilojoules, and I'm going to subtract the reactants, which is negative 74.8 kilojoules. Okay, so I'm going to take this number and subtract it by this number, and to 3 sig figs, okay, it ends up being 802 kilojoules, but it's a negative sign, which means that that energy is being released. Okay, so when I was lighting those methane bubbles in my hand, okay, energy was being released, and I actually felt the heat come on my face and on my hands as I was holding those bubbles. And if you haven't seen that video, just go to the previous lesson to watch that, because it's a pretty cool demonstration to watch. Okay, so what we know is the enthalpy change for this chemical reaction is 802 kilojoules of energy release, because it's exothermic and it's releasing the energy. Okay, the next problem that we're going to deal with is, well, what happens if I don't have, a full mole of methane gas that's going to be reacting? What happens if I have a portion of this chemical reaction? For example, what if the amount of bubbles that I was holding wasn't a full mole of methane, but let's say it was only 1.50 grams of methane? Well, remember, enthalpy is an extensive property, which means the amount matters. Okay, the more methane bubbles I had in my hand, the bigger the heat that was being released was taking place in that kind of demonstration that I showed you. Okay, so the first thing that we're going to do is we're going to convert these grams into moles. So grams of methane into moles of methane. Okay, and carbon weighs 12 and the hydrogens are 1, so 12 plus 4 is going to be 16 grams per mole. Okay, and then I'm going to convert these moles of methane into energy, okay, using the number that I just calculated from my textbook. So there is 802 kilojoules of energy released for every 1 mole of methane. And if you do the calculations here, it ends up being negative 52.6 kilojoules. Okay. Now, I do want to show you one more problem, because there's a common mistake that students make. Okay. So I can use any one of these chemicals to figure out an enthalpy change. If I'm using a reactant, we're talking about how much is being reacted, and because so much is reacted, there's going to be so much energy released. Okay, or I can use any one of these products, and as I produce that amount of product, there's going to be an enthalpy change for how much energy is going to be released. So in this first problem, I said, hey, what if 1.05 grams of methane reacts? In the second problem, I'm going to say, well, what if 4.25 grams of water is being produced? Okay, well, we kind of go through the same process. The first step is to convert those grams of water into moles of water using molar mass. Okay, when I do the molar mass of water, this is 16, each of these are 1, so it's 18 grams per mole. Okay, and then I'm going to convert those moles of water and convert it over to energy. Remember, there's 802 kilojoules of energy that's released, but it's not per 1 mole, because when we're talking about water in this chemical reaction, it's for every 2 moles of water that's produced. So the big mistake that people do is they like to put a 1 here, just like I did here. But the reason I put a 1 here was because the coefficient was 1 in the chemical reaction, okay? Well, for water, the coefficient is not a 1, it's a 2. So I have to put a 2 there, okay? Because 802 kilojoules of energy is released through the production of 2 moles of water. So make sure you match up your coefficients when you do this energy to mole conversion. And you have to follow the amount of moles in that chemical reaction, okay? So if I do the math here, 4.25 divided by 18 times 802 divided by 2, remember the negative sign, so that's going to end up being negative 94.7 kilojoules, which means 94.7 kilojoules of energy is released when 4.25 grams of water is produced according to this chemical reaction. Okay, I'm going to have a couple more practice problems in the next video where we deal with not just grams, but we're going to talk about molarity and also using the ideal gas law in combination with the stuff that we just learned here today. So if you find this information useful, please give it a like and subscribe. Even adding a comment telling what you liked most about the video will really help distribute this information to other students that are interested in learning chemistry.